So on this, on the screen that you see right now, what I did to make this was I just made a little slideshow that goes basically forever through like 6 pictures of EVCC that I could find on the internet. And I swear I thought when I put all these in here that they were all like clear, no clouds in the sky. And now that I'm looking at them, I'm like, you know what? I think that one's actually like overcast. These are all found pictures on the internet. I didn't take any of these. Although I have actually thought about doing so. Also, this music totally fits Everett Community College for some reason. Like, trapped in the late 70s or early 80s. I feel like Vaporwave and EVCC go together. Alright, that's enough of that. Let me wind this down here. So, the soundtrack we have for this week is Paradise Killer. This might be one of my favorite soundtracks ever, because I do love Vaporwave. And if you are interested in a murder mystery where you decide the outcome based on what you discover, it is a fantastic game. I got absorbed by that game world for probably like a week and a half, 2 weeks. I spent just wandering around learning everything I could, and then I had solved the mystery. There's multiple mysteries, for what it's worth. To a convincing argument that I felt like, yeah, this is what happened. Because there's really no... The game is set up in such a way that, as the investigator, you basically get to determine the outcome. Like, you present your prosecution based on what you have found. And the person who judges that bases whether you have found a satisfactory amount of evidence or not. So you can prove anything you want to as long as you have enough evidence. When we know our lab scores, we get to turn in the lab first. So labs are due later this week. So you can see at the bottom down there. Lab worksheet number 1 is due on Wednesday the 20th. Quiz scores I need to go through and release. I'm going to do that later today. I was going to do it last night, and then I realized that I had a different issue with a different class. I try and do them all at once so I don't have to go in Canvas like 63 times. So I believe that issue for 161 has been resolved, because they also have a quiz, but I had to tinker with it in some way. So now I'm going to go through and just tell everything like, okay, if all the dates have passed, you can release all the scores. So what else do we have? Quiz number 1 was due Thursday the 14th, so I don't need that up there anymore. So yeah, your quiz has been finished. I can release those scores, but for the unforeseen reasons that I didn't do that yet. So let me just get rid of that, because boop, that's done. There we go. Okay. We're going to finish chapter 2 today. Oh, I need the tablet. I need to be able to write. Let me grab that. So for the exercises today, we're going to start by doing problems that are slightly more complex than what you have done before. So at this point, you should be able to do basic conversions if you can look up the conversion yourself. So for instance, if I asked you to convert like something in meters to something in yards, and you went to Google and said, okay, how many yards are in a meter? You could then do that conversion. Or if I asked you like how many millimeters are in 74 miles, you could do that, because you go miles to kilometers, kilometers to meters, meters to millimeters. Those are all known conversions. For these problems, what we're going to do is we're going to use known conversions, but we are also going to throw in unknown conversions, in the sense that they are conversions that are unique for a given problem. This is very often the case in chemistry, especially in healthcare. You are going to be using conversions that you cannot look up on Google reliably. For instance, how many milligrams of acetaminophen is safe for a child to have? That's going to highly depend on their age and their weight. I would not trust Google with that information, because that sort of stuff is all over the place. And it could be any number online, right? So as a medical professional, you have a research document, or the lab knows how much you're supposed to do, and they'll give you a conversion. So it's not a known conversion in the sense that like Google knows it and you can look it up. It will be unique to the problem that you were given. So you're going to have conversions like that in these problems. The strategy that I offer here is what I call the unit map. The unit map is a blueprint for you to try and solve a problem. Let's put a problem on the board here, just as an example. To try and solve the problem by getting from a starting point to your end point. And so, for instance, suppose that I had to convert 525.8 kilometers to inches. So what you would do is you would say, okay, here's my starting point, here's my end point. What do I do to get there? Because the direct path may not be obvious, or you might think of a different path than anybody else does. Here's my suggested path here. So kilometers to meters to centimeters to inches. And so you can look up all of these conversions. So for instance, in 1 kilometer, there are 10 to the 3 meters. Or in 1 centimeter, there are 10 to the minus 2 meters. Or in 1 inch, there are 2.540 centimeters. So those are all things that you can look up. And by blueprinting them out like this, you can get a little map going and say, okay, now I know what conversions I need to do to solve the problem. Because all you have to do is make the units cancel out. And of course, you could just flip these however you need to orient them in your problem. Now, you could also have mapped out something like this. I'm going to turn kilometers into miles, which I'm going to turn into feet, which I'm going to turn into inches. And then you'd have a different set of numbers here that you could blueprint out to solve. So for these problems, I'm going to draw the unit map out. But if you are stuck on a given problem, what I want you to do is write down your starting point, write down your ending point, and just try things. Because if you don't know what to do, write down any conversions that you can think of. And then write down any conversions that you can think of for that part. So I could turn centimeters, I don't know, millimeters, etc. This can turn into feet. This could turn into yards. And your goal is to get to here. And if you could find anything that you can turn into inches, like that works and that works, follow that path. And there's an answer. Any path that you can use to get there is valid. Let me go back and answer these questions. How do you fill out the lab? Review the directions on how to fill out the lab in the lecture that we did last week, so it'd probably be week 2 Thursday. We did a little bit on how to access that file. There is also a document that says how to download and upload lab worksheets to Canvas. Read over how to do that. It will tell you what to enter your answers into. Would I accept kilometers to meters to inches? I would accept that. I just don't use meters to inches as a conversion myself because I don't know it off the top of my head. I know meters to centimeters, and I know centimeters to inches because I use those most often. But yeah, you can skip any of these steps. That's fine. When you are drawing out your blueprint, what's important is that you have a connection from the start to the finish, whatever that connection is, and that you know all of those conversions. So, for instance, this connection here, kilometers to meters to centimeters to inches, I know all of those, so that's what I would use. But others do exist, and they may take longer paths or shorter paths. So your job is to just map out your units such that you can find a way to your goal. All right, so let's do a problem, and we will try to apply this. Now, if you're given a conversion in the problem, so this right here, You do not want to start the problem with a conversion unless you are, other than one exception. We'll talk about that exception in a second. In your problem somewhere, there will be a number that is the constant. And generally speaking, your problem will be asked in a way such that how many of this thing are in number of units? And that number is what you want to start the problem with. So for instance, here's a simple problem. How many hours are in 2 years? There's only one number here, so we're going to obviously start with 2 years as our starting point. And then our goal is to figure out how many hours are in that quantity. So let's try this. So here's my starting unit. And I'm going to write that down right here. So I'm starting with years. And the problem is asking us how many hours are in there. Do you know how many hours are in a year? I sure don't. So I cannot just go directly from years to hours. But what I do know for hours is I know how many hours there are in a day. I know how many minutes there are in an hour. But minutes is getting smaller, so that's not going to help me. I want to get to bigger things, right? So I know how many hours are in a day. There's 24. How do we get from days to years? Because you could do something like this. You could do weeks. You could do months. Although days and months is not so great because all the months aren't the same length, so this is probably not ideal. Or do you know how many days are in a year? That's pretty common knowledge, right? How many days are in a year? So we could do something like this. So here's our blueprint. So we're going to do something like this. And then anything else that's like dangling off of this that we don't need, we'll just erase it. So we don't need weeks in this problem because we've already found a route. Now, don't worry about where the arrows are pointing. The arrows are just for our convenience to help make our map here. When we do the problem, we're not going to use the map for our calculation other than to say, okay, here's where I started, so I'll go to the next thing connecting it. So when you set up your units, put in the units for your connections, and then they'll cancel out. Okay, how many days are in a year? I'm going to write down this real quick. So that's how many days are in a year, right? Unless it's 2024, in which case there's an extra day, right? What about leap year? Which year is it? Could one of our 2 years be a leap year? In fact, there's no way of knowing. So what we do is we actually do this. That way every 4th year gets an extra day. Or in other words, there is a quarter of a day added onto each year to accommodate for leap year. So that's how many days would be in 2 years. And then I know that if I do this, so now I've done this conversion. How many hours are in a day? Well, in one day there are 24 hours. And so there you go. So now I can just punch all this in the calculator. And round it to 2 sig figs. All right. This is the lowest of them. This is 5 sig figs. 5 sig figs. This and these are all exact. So that's how we would solve this type of problem. Now, this is a simple problem, so Google could answer this for you. But I'm not going to ask you all simple problems. I'm going to ask you more complex problems that you won't be able to type into Google because they're just too long. Google won't recognize it as a calculation, and instead it will just ask you, like, oh, is this what you meant to search for? And that's not super helpful for you. All right. Let's do another. What is the Sig Fig rule again when rounding? Round to the nearest. So since I had 17,532 here, and I only get to keep 2 sig figs, I would round this next digit. 5 or higher rounds up to 8. Oh, I gotta click over here first. There we go. All right. I'm gonna give you a different problem here. I drive on the highway. When I had a Harley, I don't have it anymore. I donated it to charity because I didn't want it anymore. I had nowhere to keep it. I drove 75 miles an hour down the highway. How many minutes will it take me to drive 20 miles? Now, here I have 2 numbers. I have this number and this number. One of these is a conversion and the other is a value. Which one is the conversion? How do you know? And the answer is, look for the one that has per or a division symbol in it. This indicates the conversion. And what that means is that this links 2 units together. So if I know how many miles I've gone, I know how many hours that will take me. Likewise, if I know how many hours I have driven, I know how much distance I've covered in that time. Because if I'm going 75 miles an hour and I drive for half an hour, I would drive half that distance, right? 37.5. Likewise, if I drove for 3 hours, I would drive 75 times 3 miles. So when I say conversion, I mean that it is a conversion in the problem that will convert 1 unit to another. Now, how will that help you? It depends on what numbers I have given you for the problem and what your goal is. So for instance, for this specific problem, we can see that the speed that is shown will convert miles to hours. So if we ever get to a place in our problem where I need to go from miles to hours, that will help us. Now to start the problem, I want to use the value. Which of those is a number that is just a value with a unit all by itself? And that number is this. So that's where we're going to start. And the units of that are miles. And what is the problem asking us to do? How many minutes will it take me to drive this many miles? So my goal is to get from miles to minutes. So how do I get these to go together? How do I connect from miles to minutes? If you type in Google, how many miles are in 1 minute, it's going to ask you, like, what are you talking about? You need to tell me how fast you're going, or something like that, right? Now, on the screen, you can see that I've circled the miles per hour up there. So hours to minutes, that's a good start. I know how many minutes are in an hour, so if I know how many minutes I've gone, I know how many hours I have. And then you can see up there in red, I know how to convert between miles and hours because this problem gave me a speed, right? In 1 hour, I would drive 75 miles. So now I have my map. I can do that by writing it out like this. So I'm going to convert miles to hours. And in 1 hour, I would drive 75 miles. And then I would convert hours to minutes. And in 1 hour, there are 60 minutes. And there you go. So that would tell me how many minutes it would take for me to drive 20 miles at this speed, which would be 20 times 60 divided by 75. I wrote miles, but I meant to put minutes. And there you go. So we needed a conversion to solve this because miles and hours are not units that are typically linked together. One is a distance and one is a time. I can't convert times into distances without a conversion factor. And the conversion factor that was given was 75 miles per hour. Now, if I asked you a different problem, you would get a different answer. And so that's what I meant by unusual or unique conversions. They're problem specific. You can't look up the speed that this motorcyclist is going on Google. Google doesn't know who this motorcyclist is. Trust me, I've looked. So sometimes you won't just be able to put a problem into Google and get the answer. You'll need to use the conversions in the problem to solve it. And those conversions will always have a hint like this. So there'll be this slash to indicate that it's per something. Or I might even write the word per. Did YouTube hiccup? You're going to have to be more specific than that, or rewind, because I'm not sure what you mean. So always look for this per symbol when doing these types of problems. I'm going to give you a different problem here for you to do. Oops. We got to go back here, though, for you to see it. So what I want you to do is tell me the answer to this problem. I have a puppy, and his name is Scoots. I don't actually have a puppy, but Scoots eats 65.3 grams of kibble every day because he's a growing puppy. How many pounds of food will he have eaten in 35 weeks? So I have given you two numbers. One of these is the conversion. Which one relates two things together with a division symbol? Notice that I have not used the per word in here, but I've implied it somewhere. So I'm going to give you a second to play around with that. I'm going to go get more water because I drank all my seltzer water here. And we'll go over the answer in about 5 minutes, okay? See you in a bit. 1 more minute, we'll go over the answer. You want to say hi? Yeah. Bye. Bye. Yeah. Say meow. Bye. Maya doesn't want to say meow today. She just wants to brush on the microphone here. All right. So it's my time. Yes. Yes, it is. She came up to say hello. She was meowing a second ago, but now she's not. Oh, there she is. Can you hear her? If I look away and then I look at her. Maya. There we go. That was a good one. Hopefully you heard her. I'm not sure if I would call it performance anxiety for Maya. She's just so excited because I'm sitting in the chair and that means I can pet her. All right. So in this problem, we have our conversion factor is that she eats 65.3 grams. Not she, sorry, Scoots eats 65.3 grams of kibble per day. And that I'm given 35 weeks for the starting point of my problem. Oh, Maya ran away. Okay. So, if I'm going to map out my units, I'm going to start with weeks. And then I'm going to end with whatever the problem is asking us. I want to know how many pounds of food we have. Sorry, seltzer water. Ah. So what can I convert weeks into, and what can I convert pounds into, and how do I connect these two? Remember, I have this conversion, so I can turn days into grams. So I should probably turn weeks into days, right? And if I do that, I know how many grams I have eaten. Well, that Scoots have eaten. And then I know how many grams are in a pound, so there's our goal. So this would work. And yes, cats are better than dogs, but you know what's better than both? A pig. I really want a pig. I want the biggest pig that will just, like, run around in the backyard. Of course, I would need a backyard. Because I live in an apartment, and that's miserable, and I hate it. Oh, ducks are adorable, too. So we're going to turn weeks into days. How many days are in a week? Well, there's 7. Why 7? I don't know. Someone decided that. We're going to turn days into grams, which is a very weird unit, right? But every day, Scoots will eat this many grams. So that unit makes sense for this problem. And then, how many grams are in a pound? We can look that up on Google. There are that many grams in 1 pound. So this would tell me how many pounds of food Scoots would eat. I've heard about bearded dragons. I like lizards and reptiles myself. I have a friend who has, like, a ton of snakes, and his snakes are all really cool. But unfortunately, they don't get, like, let out of their cage much anymore because they're so busy. So I got 35.3. I only get to keep 2 sig figs here. So this is 2 sig figs. These are exact. This is 3 sig figs. And this is 4 sig figs. So my answer should have 2 sig figs, and I would write 35 pounds. Where did I get 453.6 grams? I use Google for that. So if I Google pounds to grams, Google shows me this. Let me capture the window real quick. Boop. Well, I mean, that's not super helpful, but so when I typed it into Google, I got that. 1 pound equals 453.592 grams. And so, like, for any conversion where you're like, hey, what is this conversion? If it's the same type of unit, so, like, these are both weights, right? Or masses, you could look that up on Google. On any quiz or exam that you need to look it up, you're free to do it. I don't restrict you on your exams in this course. You can use the internet for any purpose that you want. However, for things like conversions, I would have all of that handy. Like, maybe have a browser tab open with this window right here so that you could put in the units that you want, rather than just, like, trying to type in stuff into Google and searching the internet, because, one, you're timed very strictly, and two, Google is its own little, like, pit of hell that you can just get sucked into. And, oh, hold on, I'm dropping frames. Okay, I think it's fine now. And basically it's a black hole of just knowledge and information, and you don't want to get sucked into that during an exam, so. All right. So there was our first problem. Here's our second problem. So we said the cats are better than the dogs, so here's the cat problem. This is Hazel. Hazel has sprained her paw, and we needed to take her to the vet. And the dose of aspirin that was recommended by the veterinarian is that 3.67 milligrams of aspirin can be administered per kilogram of kitten that you have. How many milligrams should I give to Hazel here if Hazel weighs 2.41 pounds because she's so small? Now, this actually isn't actually Hazel, but I did have a calico cat named Hazel, which is why I named this cat that. Hazel lived to be 22. She passed away like 4 years ago, and she was ancient. And then immediately after Hazel passed away, like, I didn't even have a chance to mourn. A friend of mine said, I'm moving and I have these 2 cats and somebody has to adopt them because I don't want to see them go to a shelter. And I can't take them because no apartment will accept pets in Seattle because Seattle's fucking stupid. And I immediately was just like, I will adopt your cats. My cat just passed away. This is apparently something I do, is I adopt other people's pets that they can no longer take care of so that they don't go homeless. And that's how I got Maya and Kresnik. So, if you want a pet, go to a shelter. Adopt an animal that needs a forever home. That's my heartfelt recommendation, because look at Hazel here. Now, very importantly, make sure you solve this problem correctly. Don't overdose my cat, okay? I'm gonna give you 5 minutes to determine how much aspirin you should give to Hazel for her paw pain. It sounds so dumb. All right, I'll be right back. 1 or 2 more minutes, and we'll go over the answers. I just saw that somebody made the pets channel in the Discord, so just very appropriate. All right. Now, very importantly, it's time to find out, did you overdose my cat? I guess we'll find out, right? All right. Oops, that's the wrong problem. Sorry, there we go. All right, so we have on the board here, we have a mass of cat, not IV cat. And the cat weighs 2.41 pounds. And we can administer 3.67 milligrams of aspirin per kilogram of cat. So we should actually be specific here because we have masses of different things that we want to coordinate. So I have a weight of the cat in pounds, which I can turn into kilograms. And if I know how many kilograms the cat weighs, I know how many milligrams of aspirin to administer. And that's what I want, right? So how many pounds are in a kilogram? I don't actually know that one. I have to look that one up on Google. I think it's 2.204 or something like that. So 1 kilogram is 2.205 pounds of cat. And I know from my conversion that if I have some mass of cat, I can give that cat a certain amount of aspirin. So for every 1 kilogram the cat weighs, I can give them this much aspirin. Pounds of cat. Here's a better one. So we'll cancel out the cat. The cat is now canceled. And so now I just got to punch all these numbers in. There you go. And then we check for sig figs. So we got 3 sig figs. This is 4. This is 3. 3 is the lowest. So our answer should have 3. There you go. Yep, we canceled the cat. The cat is canceled. So there's our answer. We'll go back over here. And we'll cancel the cat. There we go. No, I'm just kidding. Nobody cancels the cat. The cat is the best. All right. Here's more problems for you to try. I don't know why my screen is flickering there between the cat. So the first problem is pretty standard. You just need multiple steps to get through it. But the second problem and the third problem... Oh, okay, the third problem is actually just as easy. But the second problem has a unique conversion, and that's this. Salt does not cost $10 a pound. Don't be ridiculous. Is the first fraction what we're converting to? What you're converting to should be whatever the problem is asking you. So I want to convert to milligrams of aspirin using this number to start. And so that's what we did there. So you pause the video if you need to see that. I had to cough there, sorry. Had to hit mute. All right, so the next problem set here, these first three problem, or I'm sorry, the first problem and the third problem are pretty straightforward. The second problem, however, has the conversion in it, which you'll have to do. So if you're going to do one problem from these three, do the second one, and then try the first one and the third one. So I'm going to give you 5 more minutes to do these 3 problems. Then we'll go over the answers, and then we'll take a break. I haven't played World of Warcraft in forever, but when I made these slides, I was playing it, so all the WoW references just stick around. Let's do 2 more minutes and we'll go over the answers. All right, so we'll do this. We'll put these on the screen here. I'll just get these 2 for now. All right. Oops. I don't know why that didn't work. There we go. Okay. All right, for the first problem, very straightforward. I have 30 km, and I need to go to miles. Now, there's a direct conversion from kilometers to miles, so there's really not much that you have to do for this problem. So a mile is, I want to say 1.609 kilometers, but let's see. 1 mile to km. Yeah, 1.60934. So when I do that, I get 30 over 1.609, 18 something? Yeah, 18.6. So that one's real straightforward. The next problem is much more complex. So if salt costs $10 a pound, how much would I pay for 15 kilograms of salt? So I have 2 numbers there. One's a conversion. The other was where we start. So if I know the number of kilograms of salt, I then know its mass, and I want to get to money. So what I need to do is, first of all, I have a conversion for dollars to pounds, so I need to turn kilograms to pounds so I can then turn pounds into dollars, right? All right, so we can turn kilograms into pounds. Let's see here, mass, pound, kilogram. So in a kilogram, there are 2.204, not 4, sorry, 5 pounds. And then I know that I can pay $10 per pound of salt. How much could a pound of salt cost? $10? For this problem, yes. Yes, it does. What are we buying? Bananas? $331 is what it would cost to buy that much salt at this rate, which I think is kind of a ripoff. You can get salt a lot cheaper at the store. And then for the last problem, let me get the troll up here. All right, so this troll weighs 325 pounds. How much does he weigh in milligrams? So we've got pounds, and we need to get to milligrams. So to go from pounds, so I can do pounds, grams to milligrams. That seems like the fastest way. And so there are 453.6 grams per pound, which I can find that information on Google. And then I can do a milligram, 10 to the minus 3 grams. Times 10 to the minus 3. 3, 6, 7, 8. Okay, so 1.474 times 10 to the 8 milligrams. It's a lot of milligrams. It's also a lot of troll. I'm an orc guy myself, but trolls are the good guys. It's the humans you gotta watch out for. All right. Any questions? Let me know. Yeah, inflation is out of control. We're paying $10 for salt, right? All right. We're gonna go back to. Oops, wrong button. I'm gonna click over here. We're gonna go back to listening to some Paradise Killer. Let me get the timer on the screen here. And oops, hold on. I have the wrong window open to do this. There we go. Oh, it idled. Hold on. I gotta tell Google not to do that. Sorry, technical difficulties here. Never suspend this domain. Do not suspend the YouTube stuff. Okay, perfect. All right, so that should work now. And now when I hit this button, you will have lovely music. All right, we're back. So the next section, what we're going to talk about is a little bit on a topic called density. Density is a conversion factor, just like all the conversions that we were doing in the previous section. It is going to allow us to convert between mass and volume for whatever substance is in question. Every substance has a density. Whether it is pure or a mixture or whatever, you can calculate the density by using this very straightforward relationship that we're going to present on the slides coming up. So, if you have looked at objects that are maybe small in size and then tried to lift them and you're like, wow, that's surprisingly heavy, like, say, lead buckshot that's used for loading shotgun shells. Yes, my family is a redneck family, so I know exactly what this is. My bedroom at home got turned into the reloading room, if that tells you anything about my family. Family of hunters, or so they claim. But lead is particularly dense. If you have seen like lead pellets, and you've tried to lift it, or you tried to lift it, it's remarkably heavy for its size. On the opposite side of the spectrum would be things like this Darth Vader balloon, where it occupies this tremendous volume, but the mass of the gas inside is actually remarkably light. So the relationship between these objects is the density of those objects. The density is just how much mass there is in a given volume. Densities can go from very, very, very little to absurdly ridiculous. For instance, if we were looking at the density of just like gases, they're roughly a few grams per liter. Like a liter is a lot of volume. A 2-liter bottle would have like a gram of gas in it, which is not really that much in reality. If you want to consider the densest thing known, that would be something like a neutron star, where a teaspoon of a neutron star weighs on the order of billions of tons. Not kidding, like insanely dense. Most substances that we will work with or encounter will have a density on the order of 1 to about 20 grams per milliliter. Oh, excuse me. All right. Oops. Now, if you put multiple substances into a container, and those substances have different densities and they don't dissolve in each other, those substances will sort based on their density. And I'm going to show you a video of that in a second here. Actually, you know what? We'll just show that video right now. So let me find the density video. Density tower. Let's show you the density tower. Here we go. So let me get this on the screen. So what we're going to do is, for this video, oops, not much of a video, I just show you part of it here, I guess. There we go. So what we're going to do, I'm going to cover up the chat for a second. How do you measure the density of a neutron star? You don't measure it, you calculate it. Nobody is out there at the neutron star going, scoop, and they're like, oh, there we go. Weighs 1 billion tons. All right, so here's our density tower. There is audio for this, which is kind of annoying, but that's okay. I'll play the music over it, or talk over the music. All right, so what we're going to do is we're going to mix all of these things in a tower, but in an order so that they don't actually mix together, and then we're going to add a bunch of things to it. We're also going to add adult supervision, which is stupid. Oh, sorry, hold on. That's what I wanted to pause on. So there are all my substances right there. So we have honey, corn syrup, maple syrup, whole milk, dish soap, water, vegetable oil, isopropanol, and lamp oil, which I suspect is kerosene. We're going to mix them in this order. Food coloring has been added to the water and the rubbing alcohol, and I also suspect the lamp oil, so that you can see them. And then we're going to pour them into this tower one at a time. So here we go. Go slow. Now, if you pour these in carefully enough, what you'll notice happens is that they all separate out very nicely. And then when we drop these objects into there, they fall based on their density. And so here are all of our objects sorted by density. So all the liquids separated out and are arranged by density. If they were not, now we had to put the liquids in there in that order. If we put in a liquid that's had a density higher than something below it, it would sink through. So we have put these in this order because of their density. The objects themselves, however, so all the things listed in red on the right, those were just dropped in, and so they just sink to wherever their density is appropriate to be between something that has a higher density than it below and a lower density than it on top. And so, for example, right here, the beads have a density that must be less than water because they're floating on the water, but higher than the vegetable oil because they sink to the bottom of it. The dice sunk all the way down to between the milk and the maple syrup. The tomatoes are mostly water, right? So there's other stuff in there, so it's going to be more dense than water, but not as dense as dish soap, for example. So that's the density column. Everybody has fun with that one. You can make this at home if you want. But the point is that you can make things float based on their density. All right. Here's our equation for density. This is going to be a very useful equation for Chapter 2 and also for your lab because there are going to be some problems in there that ask you about density. And if you know any two of these terms, you can solve for the third one. So our task is going to be to solve a bunch of these problems where I give you two of the things and you have to solve for the third thing. Now, depending on which one I have you solve for, this expression becomes more difficult. So we can rewrite the expression as this. D equals M over V. And you're going to have to solve for either D, M, or V based on what the problem is asking you. Now, before I go to that part, I want to write down here, so let's say units. For density, depending on the phase of your substance, the units tend to be a specific standard. If you are working with a solid, the units of density will be in grams per cubic centimeter. What that means is that your mass should be in grams and your volume should be in cubic centimeters. Because those are the units that are shown up in density, right? For liquids, the standard is grams per milliliter. And so the same thing, mass should be in grams, but volume should be in milliliters. And then finally for gases, gases are typically grams per liter. Now, most problems will specify the units for you and then ask you, I want density in these units. To make the problems more difficult, you may be given other units for your amounts. So I might say like, oh, okay, I have this object that has a mass of 38 pounds and its volume is 2.5 gallons. Figure out its density in grams per milliliter. So you'd have to turn pounds into grams, and you'd have to turn gallons into milliliters, and then divide the two to get the density in grams per milliliter. So just be mindful of that you may have to do conversions here, and in fact, that's the exercises that we're going to do. So this first one is very straightforward. We're going to do grams per cubic centimeter because we have a metal, and metals are solids, right? Osmium metal is the most dense metal that is out there. Osmium weighs, this sample of osmium that I have weighs 26.3 grams, and its volume is 1.16 cubic centimeters. What is the density of osmium in grams per cubic centimeter? Very straightforward. Not even going to turn you loose to do this problem because we know that density is mass over volume. And here's the mass right here, 26.3 grams. Here's the volume, 1.16 cubic centimeters. And then what I want to do is I want to actually punch this in my calculator to get a number. And then the units stick around because they didn't cancel. And there you go. Easy as that. So if you are asked to find the density of something, it is as simple as what is the mass divided by what is the volume. The tricky part is making sure that you have the correct units available. And if you don't, you'll have to convert them. For the next problem, you will have to convert something. Oops, so there's our solution there. All right, here's the next one. Actually, you don't have to convert something here. But for this one, I want you to tell me, what's the mass of helium in a balloon if the volume of the balloon is 2.5 liters and the density of helium is 0.1786 grams per liter? So mass of the helium balloon in grams. This one I'm going to let you do. So I'm going to give you 4 minutes to try it. We'll go over the answers in just a second. One more minute, we'll go over the answer. All right. So to solve this, what we need to do, we're going to write down the density expression first. For this, I am given the density and the volume, and I need to solve for mass. So let's multiply both sides by V to get this. So now if I have density times volume, that will give me the mass. And so let's write that all out. So the density was 0.1786 grams per liter times the volume, 2.5 liters. You'll notice that the volumes cancel out, which leaves you with a mass. That's what you want. So let's do the calculation. I get 0.4465 to 2 sig figs, that's 0.45. All right, very good. Lots of people got that one right. All right. I need to clear my screen. You can pause the video if you need it again. So there we go. All right. Here's the challenging problem. I have a glacier with mass 46,720 kilograms. The density of ice is 0.9899 grams per milliliter. What's the volume of the glacier in liters? Be careful with your units. That is a warning. So make sure that you are not messing up the units here because you want them to match and you immediately see a mismatch, right? So what I'm going to do is I'm going to let you try this for 5 minutes. I'm going to write down the density expression. Make sure you're solving for the correct variable, but make sure that you are solving for it where it's on the top of the expression. So if you're solving for V, hint, you're solving for V. Don't just divide both sides by M. That would be wrong. Okay. Be careful with your algebra. Go ahead and try it. I'll give you 5 minutes. We'll go over the answers in a bit. One more minute, we'll go over the answer. All right. So we're going to go to this screen for this problem. Maybe not like that, though. All right. Now, this is a glacier, so you should be getting a glacier-sized number, right? It should be big. So here's our expression, density equals mass over volume. And I know the mass, right? And I know the density. I need to solve for the volume. So what that means is that I need to rearrange the expression so that I have volume by itself. So first I have to multiply both sides by V to get that. That's how we solved for mass earlier. Then I need to divide both sides by D to get this. So there's the first step. We need to do algebra to isolate this V, right? But you have to get it on top of the expression first. If I divide both sides by M, I would get 1 over V, and that's no good. So now I can just plug in the mass and the density. However, the units don't match, right? I need kilograms or grams. I'm going to convert this one to grams. So there would be my volume, or my mass in grams. Now if I plug in all these numbers, let's see what happens. So volume equals mass divided by density. So our mass we got was that many grams. And the density that we got was 0.9899 grams per milliliter. Now, this is kind of weird. These units right here, kind of strange, right? This is where our algebra skills kick in, right? If I have something divided by a fraction, here's my fraction on the bottom. That's the same as doing what with this fraction? If you divide by a fraction, it's like doing what? I'll give you a hint. You have to multiply something. Dividing and multiplying are not the same, but there you go, multiplying by the reciprocal. What's the reciprocal of A over B? It's B over A. And then the A's cancel, and you get that, right? So if you divide by something, That is a fraction. It's like multiplying by the reciprocal. They are the same thing. So here I have my units. Let's get rid of this real quick. Here are my units that are in this problem above. I have grams divided by, parentheses, grams over milliliters. So that's like multiplying by the reciprocal. So the units of everything that's circled in blue up here cancel out to become milliliters. So when I punch this in the calculator, the units that I get out will be milliliters. So there's the volume of my glacier. However, the problem asked me, hey, I want you to turn this into liters. So now I need to take that number. We'll just get rid of that. And we need to turn it into liters. And I know that in a milliliter is 10 to the minus 3 liters. There's the volume of our glacier in liters. Yeah, you had the right number, but you had the wrong units at the end there. Your answer was in milliliters, actually. So yeah, you always got to check your units. So be careful. Remember, your units are telling you what your number represents. And so the units are super helpful. If all you were doing is plugging in the numbers and not writing down units in your steps, you'll get stuck. You'll get the wrong answer every time. Especially on the quizzes, because the problems you're going to see on the quiz are more like this one than the previous ones. Yeah, this is one of the harder problems that we have in this chapter. One of the hardest, I should say. All right. I'm going to give you a simpler problem for your practice problem here. And then we're going to talk about temperature real quick and we'll be done. So, I have a mystery metal. My mystery metal weighs 17.3 grams. I put it in a graduated cylinder and here's its volume. What metal is it? Now, this is sort of my segue to, hey, periodic table. We're going to be using it because we're going to use it on Wednesday. Or Thursday, sorry. Tell me which metal it is. Note that you might get a number that is not exactly these answers. Pick the one that's closest to it. I'll give you 2 minutes to do this because this is straightforward. We'll go over the answer in just a bit. All right, let's go over the answer here. So if I take my density here, I punch in the calculator, I get 21.62, or 21.63 actually. So there's my density. Which of those is that closest to? This one. So that means that I must have a platinum cylinder and that platinum, oh, excuse me, is the mystery metal. All right. So you can do all sorts of different problems with density. They're going to be of varying difficulties. I want you to do as many of these as you can from the textbook because you're going to see density problems on your quiz that's going to appear tonight. All right, any questions, let me know. Let's talk real briefly about temperature. Something to note, I'm not going to do this section here, this heat section, so this is not something we actually cover in this class. I just haven't removed these slides because why bother? I might need them again. Earlier editions of the textbook had this section, and I've since removed it. So there are 3 temperature scales that we care about in chemistry, and those 3 scales are these 3. Fahrenheit is not super helpful in science because the numbers are dumb. Celsius and Kelvin are going to be the scales that we care about. So these 2 scales are relevant for science. Fahrenheit is just garbo, and we don't like it. Fahrenheit has one real purpose, in my opinion, and that is to confuse Canadians. Hey, what temperature is it down there in Washington? Oh, yeah, it was so hot today. Oh, how hot. It's been real warm here in Canada. Yeah, here in the US, it was 60 degrees out. And then the person in Canada goes, holy shit. Because 60 degrees is like 125 or 130 Fahrenheit or something absurd like that. And then they're like, it was only like 16 today. And you're just like, oh my god, that's so cold. But in reality, 16 Celsius is like 60 Fahrenheit. So Fahrenheit is just worthless and I hate it. And yet all I can do is think in Fahrenheit because that's what we've been using for so long. Celsius is what we're going to use in the laboratory. And the reason for that is because Celsius is based on water, which has very easy to memorize temperature thresholds. The first threshold is 0, which is the freezing point of water, and then the second threshold is 100, which is the boiling point of water. What about Kelvin, though? Kelvin is interesting. What does Kelvin do? Kelvin is a special temperature scale that is used for absolute zero and scaling temperatures and also formulas. So Kelvin is going to be the temperature that we use for formulas. And the reason for that is the following. So let me put this on the screen here. If I am working with a formula, and here's a formula that we're going to be using later on in the quarter. Let's suppose that I rearrange this formula so that I have temperature on the bottom here. And then when I input for temperature, I'm going to input 0 Celsius. What happens if I input 0 and it's something I'm dividing by? If you divide by 0, you don't get a number, right? You get an undefined result. You're not allowed to divide by 0 because it goes in an infinite number of times. So you get infinity as an answer, which is not a number. So you cannot do this. But 0 is a reasonable temperature, right? 0 is a number that we could feasibly go outside and hit. Like, I could walk outside when it's 0 Celsius. So what we do instead is we use Kelvin. And the Kelvin temperature for 0 Celsius is actually this. 273.15. Whatever your temperature in Celsius plus 273.15 is your temperature in Kelvin. And the reason that we have this number is because we have set the freezing point of water to be 0 Celsius. The freezing point of water happens to just be 273.15 Kelvin. And the reason for that is because, if I take my thermometer out here, if this is the freezing point of water, right here, all the way down here, is an interesting phenomenon called the lowest possible temperature, also known as absolute zero. And that temperature is defined as literally 0 Kelvin. So absolute zero is the lowest temperature. Now, what is it meant by the lowest temperature? How can you have a lowest? Well, what is temperature? Temperature is defined as how fast molecules either vibrate or move. So in the air around you are molecules. And they're not stationary because when you breathe, you're moving all of the air into your lungs, right? And then you expel them all out when you exhale. Maybe you have like an open window and there's an air current going through your room. All of the molecules are moving at any given time. In fact, if you're in a room where it feels perfectly still, the molecules around you are still moving very, 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 very fast, actually. The amount of temperature that you feel by being present in that room is related to how fast those molecules are moving. You can think of it this way. If something is thrown at you with a little bit of force, you feel a little bit of impact. But if something is thrown at you with a lot of force, you feel a much stronger impact, right? This would be like me throwing a baseball at you at 20 miles an hour and then having a major league pitcher throw a baseball at you at 100 miles an hour, right? You definitely feel the second one. Especially if you got beamed on the ass with it, which is apparently something that happened very recently. Somebody got beamed in the butt. And so that was just all the slow motion GIFs that were on Twitter for a while, I guess. I don't know. I don't even follow sports. Anyway, the point is, the faster things are moving, the more energy they have, right? So if you are being struck by molecules at room temperature, you will feel a certain amount of energy. In other words, heat. But if I turn up the heat, the molecules are moving faster. They have more energy. You feel that as hot. Likewise, if I turn down the heat and I slow down molecules, you feel that as cold. That is just the sensation that our body feels. This light energy impact is cold, and this one is hot. What if I had my molecules just not moving at all? That would be absolute zero. So absolute zero is the absence of molecular motion. So if the motion of molecules dictates their temperature, the slowest possible speed, which is 0, would be the lowest possible temperature, which is also 0 in the Kelvin scale. So that's what temperature is, and that's why we have set the Kelvin scale to be 0 at the bottom, and then whatever temperature we end up on. It turns out this is the temperature we get at 0 degrees Celsius, or the freezing point of water. And so we relate that into this formula here so that we can convert Celsius to Kelvin however we want to. Turns out that 1 Celsius and 1 Kelvin are the same thing. So if I increase my temperature by 1 Celsius, I also increase it by 1 Kelvin. They're just offset by 273.15. Fahrenheit, on the other hand, is stupid. Fahrenheit does not convert well. 1 Celsius is 1.8 Fahrenheit. And that's dumb. That's really all I have to say about Fahrenheit. The formulas I have for Fahrenheit are on the slides here. We'll just put those on the screen real quick. There they are. These are all exact quantities for what it's worth. So if you're worried about sig figs, you should be. The 32s are exact. So when you do addition, that's 32.000000. It won't affect your result. The divide by 1.8 or the times 1.8, those are also exact. You may see 9/5 or 5/9 in different formulas. Those are just 1.8. It's easier for me to typeset 1.8, so that's why I put. So if I give you a temperature in Fahrenheit, you can turn it into Celsius. Likewise, you can turn a Celsius temperature into Fahrenheit. And then if you need to turn a Celsius temperature into Kelvin, here's that formula again. There are more decimal points here. If you need 3, there they are. Typically speaking, 2 decimal points is enough. If you need more than 3, I don't really know what you would need more than 3 for, to be honest. But I'm not going to have you do these practice problems right now because we've already talked about absolute zero, so it's fine. Because these are just practice, like, put it in the formula and see. You can also just type it into Google. Google will convert the temperature from one to another for you. And that's fine. So I'm going to leave you to do that for your own practice. We are out of time for the day, so that's where we're going to stop. But this is the end of Chapter 2. So there's your temperature homework practice. And here's your dancing work. So, oh, wait, hold on now. We gotta skip ahead to this part. All right, there is actual chemistry in Chapter 3. So when we come back on Thursday here, we're going to do actual chemistry. So what I did here at the end here, so this heat section, we're not covering it. It is not in the textbook. You will not be tested on it. Everything else in Chapter 2 is fair game. I will put the quiz up for that tonight, and it will be due a week from today. So when we come back on Thursday, we're going to talk about the periodic table, which is a much, much easier subject. So if you can make it through the math that we have just all done in Chapter 2, you're going to be in good shape. So I know it's difficult. Do the best that you can. Do as many practice problems as you can, and you'll be okay. We'll make it. That's all I got. So let me hit this button to play the outro music. Lab worksheet number 1 is due on Wednesday. I will put the quiz up for Chapter 2. I'll see you on Thursday for Chapter 3. Take care.